Obviously, air resistance is far from the only mechanics problem we can attack with differential equations. Here, we are now going to look at the problem of a charge in a magnetic field. So this is a charged particle. It has mass m and some charge q, and it's moving with some velocity v right here. We also have a magnetic field present, but it will be pointing out of the screen. And under those circumstances, we know that it's going to be a force that will be applied to this charged particle. Force is like this. This is the magnetic force, so it's going to be equal to Q times V cross B. Since the magnetic field here is uniform, we're going to take B in the Z direction. So we'll say that it's just 0, 0, and B. So the field is entirely in the Z direction. That makes it easier then to calculate the total force. It's just the determinant. Which we can see equals okay, so there are two components to this force. We then apply Newton's second law. It says that the acceleration, which is really mass times the time derivative of velocity, equals the force. And this is the force that we have right there. So this gives us now three equations, because this is a vector equation. We can write it out then in component form. So we get just by reading off this. The force only has components in the x and y direction because we're taking the magnetic field to be purely in the z direction. And then we get this. We can see here that the z motion is pretty easy to solve for. We simply get that Vz as a function of t is a constant, which we're going to call V0c. That means then that the motion in z is just uniform velocity, V0z times t plus some z naught. We're then left with solving the problem in x and y. And in order to do that, we're going to first simplify things by introducing a constant, omega, which I'm going to call, which is going to be equal to qb over m. This is known as the cyclotron frequency. And this then gives us as the problems that we need to solve. Okay. Now we can see that this is a coupled differential equation. It couples the motion in x with the motion in y. And there are several different ways one can solve it. So a general solution to this that is often used for more complicated problems is to simply see that, okay, we can write it on a matrix form, this equation. And then we just change variables in order to diagonalize this matrix, and then we get decoupled system of differential equations. So that's a general solution, but we're not going to use that here. We're going to use something that is simpler in this case, perhaps, or at least gives you more physical insight. So here is a different solution, or different approach to the solution. So this consists of making use of complex numbers. And it works when you have this form of the system differential equations. I'm going to introduce this new variable eta, which I'm going to say is equal to Vx plus I times Vy. And if we have that, we also get, of course, that eta dot is Vx dot plus I Vy dot. And we can also multiply eta by an I, and then knowing that I times I is minus 1, we get this, right? Okay. All right, so knowing this, what I'm going to do is I'm going to take these two equations. I'm going to call this 1, and this is equation 2. And I'm going to take equation 1 and add it to I times equation 2. And then I get the following. So we can see that over here, we have eta dot according to this table here. And within the parentheses over here, we have I eta. So this just gives us, and that is simple to solve. This is just the derivative of the function equal to a constant times the function itself. So we know this gives us the solution. This is kind of the one differential equations that way you should know the solution by heart. A here is an integration constant, and since eta is a complex function, A is complex. And I'm going to write it on polar form. I'm going to say that eta equals V naught times e to the I phi. So what we really get then is that eta of t equals V naught times e to the minus I times omega t minus phi. That's what you get when you start from that equation. Now, of course, we know that we can write this exponential as a sum of a cosine and a sine. So this is also equal to the following. This minus sign comes from here. Right? Cosine is an even function, so if I take cosine of minus omega t minus phi, that's the same as cosine of omega t minus phi. But for sine, which is an odd function, the minus sign from in here comes out as a minus sign in front. So this is what we get. Now, we've already said that this is equal to Vx plus I Vy. Oh, there's an I here, of course, also. So now we can make this identification that Vx of t is going to be the real part of this. And Vy over t is the imaginary part. So that's what we get for the velocities. To find the position, we just integrate this directly, which gives us and for completeness, we should also add in the z motion. And there are offsets here too. And we use capital letters to indicate the offset. So this is now a circular motion. We can see that we're moving in a circle here, except that x is sine and y is cosine, but otherwise it's a uniform circular motion, the way you've seen in 2305. And then in z we have uniform velocity. So the motion is really that of a helix, where the axis of the helix is parallel to the direction of the magnetic field. I'm now going to define just the initial position of x and y, and we're going to ignore z for a while here, and I'm going to just say that, okay, I'm going to call x at time 0, I'm going to call it x0, and y at time 0, that's y0, and you get it by just putting in the numbers here. So xr0 is minus v0 over omega sine phi, where again I've used the fact that the sine is an odd function, so the minus sign here comes outside, and y0 is v0 over omega cosine phi. Okay, so if we then illustrate graphically what the solution looks like, let's make it a bit bigger. Then we are starting out at some point x0, y0, and then we are moving from this point. This distance here is r. R is v0 over omega, or given that omega, remember, is qb over m, it's v0 m over qb. This is known as a cyclotron radius, for obvious reasons, because it is the radius of the circle in which these guys are moving. The way I've done this here, which I forgot to mention, is that I actually moved the origin to exist at the point x, y, and z. So the origin here is at x, y, and z, capital X, capital Y, capital Z, so that we can take these out. And then what we have is circular motion or helical motion around the origin. And then some point later, we end up over here. So this is where we are at x, y. Now to complete this analysis, I'm going to ask you two questions. So the first question I'm going to ask you is, where is phi here? If you were to draw phi in this figure, where would you draw it? So the first question is, draw phi in the figure. Second question is the movement of this particle clockwise or counterclockwise? Now we must make note, of course, that omega here is proportional to b, so that actually, the answer to that actually depends on the sign of b, because that changes the sign of omega. So we're going to assume here that the magnetic field is greater than 0. So those are the two questions I have for you, and we will discuss the answers in class.